we want to calculate the following integral from minus I infinity to I infinity. So what do I mean by I infinity? It means that the contour of integration is the imaginary axis, so we are integrating over the vertical line. And we have to be careful here because this function, this integrand, contains a pole at z equal to 0. So somewhere here there is a pole, and I have to be careful and choose the appropriate contour of integration such that this pole can be avoided when I perform the integration. And then I also have another pole at z equal to 2, and these poles have multiplicity equal to 1. So let me draw also the real axis. This is z equal to 2, whereas this is z equal to 0. And in order to perform the integration, we also have to take into account the sign of this parameter lambda. Lambda belongs to R, it is not equal to 0, but if lambda is negative or if lambda is positive, we have two different possibilities for the contour of integration. So we have different choices, and we will see that now. In particular, we will see that if lambda is positive, we have to choose the following contour of integration. So I'm starting here from minus I infinity, and then I'm reaching the point z equal to 0, like this, vertically. Then in the neighborhood of the point z equal to 0, I'm going around the point like this, with the semi-circumference, which is traveled clockwise, and then I proceed to I infinity, but I have to close the contour with another semi-circumference whose radius is capital R. Let's call it capital R, and capital R goes to infinity. So this point here will go to infinity, I infinity. So if you want, it is IR at the moment, but when we let R go to infinity, this point will go to I infinity. The smaller circumference has a radius equal to rho, let's say, and rho will go to 0. So when we integrate over this contour, let's call it gamma, I integrate over gamma the function e to the lambda z over z minus 2 dz, I will get 0 because this contour does not contain any discontinuity. And in particular, it is easy to see that when we integrate over the larger semi-circumference, the integral over this semi-circumference will go to 0 as r goes to infinity, because this denominator will be dominant over the numerator. The only contributions will be given by these vertical lines, this one and this one here, and when capital R goes to infinity and rho goes to 0, those two vertical lines will give me the integral from minus I infinity to I infinity. And now I should be more precise here if you want, because this discontinuity here, z equal to 0, is excluded from the integration. So this is actually the principal value of the integral, which means that we are integrating over that line, the vertical line, which is the imaginary axis, but we are excluding, we are omitting the point z equal to 0, because otherwise, of course, this integral would diverge. So I integrate the function e to the lambda z divided by z minus 2 dz, and then I also have to integrate over the smaller circumference. The integral over the smaller circumference can be obtained by using parameterization. If we parameterize z, we can substitute, for example, z equal to rho e to the I theta. So the parameter of integration in this case is theta, whereas rho is the radius of the small semi-circumference where rho will go to 0. We have e to the lambda rho e to the I theta divided by rho e to the I theta times rho e to the I theta minus 2. And then I have the differential of rho e to the I theta, which is rho I e to the I theta d theta. And I have to integrate from this point here, which is located at 3 over 2 pi, and we have to go to pi over 2 here. The sum of these two integrals will yield 0. And also let me add one more comment to this, because I am assuming here that lambda is positive. Then we will also assume that lambda is negative, and that will yield a different result. But if lambda is positive, I have to choose this contour, because another choice could have been different. For example, we could have closed the contour here, where the real part of z is positive. I'm not doing that, because if lambda is positive, this exponential will decay where the real part of z is negative. Otherwise, we could not find a result if we close it here when lambda is positive. Let's compute this integral here by letting rho go to 0. So first, let's simplify e to the I theta with e to the I theta, and then we can simplify rho with the rho. And if we let rho go to 0, we have integral from 3 over 2 pi to pi over 2. Then we have e to the lambda rho, which is 1, because rho goes to 0. It also contains e to the I theta, but that will not affect the result. So this exponential will go to 1, because as I said, rho goes to 0. Then we divide by rho e to the I theta will go to 0, and then we have minus 2 I d theta, and this will give me pi I over 2. Therefore, if lambda is positive, we get integral from minus I infinity to I infinity e to the lambda z divided by z minus 2 dz equal to minus pi I over 2. Now let's assume that lambda is negative. If lambda is negative, we cannot consider the same path, the same contour as above, because we have to close the contour here on the right hand side of the vertical axis, because in this case e to the lambda z will decay. If lambda is negative, the real part of z should be positive in order for this exponential to decay. And I'm going to choose the following contour. So I'm doing something similar. I'm approaching the point z equal to 0, then I'm traveling along a semicircumference. In this case, the semicircumference is traveled counterclockwise, and then I am moving to IR, where R is the radius of the larger semicircumference, and this capital R will go to infinity. And then I'm closing the contour clockwise like this. In this case, we have a discontinuity located inside this contour, where z is equal to 2. Therefore, the integral along this contour, that I will call capital gamma, of the function e to the lambda z divided by z times z minus 2 dz will be equal to, according to the residue theorem, minus, and this minus comes from the fact that we are traveling this contour clockwise, 2 pi I times the residue of the function e to the lambda z divided by z minus 2, and we have to calculate this residue at z equal to 2. It's quite easy to calculate the residue of a function whose singularity has multiplicity equal to 1. So in this case, we simply multiply the function by z minus 2, so we get e to the lambda z divided by z, and we have to set z equal to 2. So this will yield e to the 2 lambda divided by 2. And the calculation on the left can be performed very similarly to what we did in the case lambda greater than 0, because we will have the integral over the imaginary axis, which is integral from minus I infinity to I infinity, e to the lambda z divided by z times z minus 2 dz, and then we will have to calculate the integral over the semicircumference, the smaller semicircumference, where rho goes to 0. But in this case, it is exactly the same as above, there is just one difference. The only difference is that we have to integrate counterclockwise because we are going from this point to this point here counterclockwise. So we go from, for example, minus pi over 2 to pi over 2. So when we integrate and let rho go to 0, we will have something like this. Integral from minus pi over 2 to pi over 2 of this function here. This will be the same because when we let rho go to 0, we get exactly the same result. So we get minus I over 2 d theta, and this will give me minus pi I over 2. So in here, I will have plus minus pi I over 2 equal to minus 2 pi I times e to the 2 lambda over 2. So basically, we can write down the result in this fashion. Integral from minus I infinity to I infinity e to the lambda z divided by z times z minus 2 dz. It can be written like this by using the theta function. So this theta function is simply the step function if you want. Let me sketch it here. Theta of x is equal to 1 if x is positive. So this is 1, whereas it is equal to 0 if x is negative. So here we have 0 and here we have 1. It's a very simple function. So in this case, I have to use theta of lambda because I have to discern between the two cases where lambda is positive and the other case where lambda is negative. So if lambda is positive, we found out that the result is minus I pi over 2. You can simply see it from here. Whereas if lambda is negative, I can rewrite it as theta of minus lambda. So if lambda is negative, the result is the following. We have pi I over 2 because we can simply move this term over to the right hand side, and then we have minus 2 pi I e to the 2 lambda over 2. And you can wonder also what would happen if lambda is equal to 0. Well, we could actually work out the result in the limit. We can use the limit. For example, if we work out the limit from the left, it means that lambda is negative and we let lambda go to 0 from the left. So it is slightly negative. And therefore we have to consider this result here. So let me rewrite it by putting this term to the right hand side. So here we get plus I pi over 2, and then I have to cancel this term here. Let me rewrite the equal sign here. If we let lambda go to 0, this term here will go to 1. And therefore, if lambda goes to 0, this will give me minus pi I plus I pi over 2, which is equal to minus I pi over 2. And lo and behold, if you compare this with the other case, this other result here, where lambda is positive in this case, you get exactly the same result, which is minus pi I over 2. And you also get this result if lambda is positive and we let lambda go to 0. So from the right, which means that the integral from minus I infinity to I infinity of dz divided by z times z minus 2 is equal to minus I pi over 2. And this integral can also be calculated by finding the antiderivative of the integrand. So let's try to work this out. So it could be useful to give you more insight. Let's try. So we have the integrand 1 over z times z minus 2. This can be rewritten like this. We can rewrite it by using a coefficient a divided by z plus a coefficient b divided by z minus 2. So we have to find the two coefficients a and b. We get a times z minus 2 if we put together these two denominators plus b times z, and we divide by z times z minus 2. If we write out the numerator in full form, we get a plus b times z minus 2a divided by z times z minus 2. From here, you see that a plus b should be equal to 0 because we have to get 1 in the numerator. So the term that multiplies z should be 0, whereas minus 2a should be 1. So we get a equal to minus 1 over 2, and b should be 1 over 2. And therefore, the integral can be split into two different integrals, integral over dz over z, and we integrate from minus I infinity to I infinity. We have to multiply this by minus 1/2, and we add 1/2 times integral from minus I infinity to I infinity of dz over z minus 2. Now the integral of dz over z is equal to the logarithm of z, and we can show this actually. It's not so obvious because z is a complex variable, right? We know that in general, if x is a real variable, integral of dx over x is the logarithm of the absolute value of x plus a constant, okay, but that's the main point. And when z is a complex quantity, we can simply rewrite this integral like this: integral of the differential of the magnitude of z times the phase. So it's e to the I theta, where theta is the phase of z, and we divide by absolute value of z, e to the I theta. We can calculate the differential above, so this is the differential of the magnitude of z, times e to the I theta plus I mod z e to the I theta d theta, and we divide by mod z e to the I theta. So we can simplify this with this and this. So here, this is equal to integral of d mod z over mod z plus I integral of d theta, because in this case we can simplify mod z with mod z here. So you see that we get the logarithm of mod z plus I theta, but we can rewrite I theta like this. We can rewrite it as the logarithm of the exponential e to the I theta, because logarithms are the inverse operation with respect to exponentials. And if we put these two together, we get logarithm of mod z times e to the I theta by using the properties of logarithms which are extended to complex numbers. But this is simply z. So you can see that we can rewrite the integral of dz over z as the logarithm of z plus some constant if you want. But I'm not interested in the constant. We don't need that when we have definite integrals. So this will give me minus 1/2 logarithm of z evaluated between minus I infinity to I infinity plus 1/2 logarithm of z minus 2 evaluated between minus I infinity to I infinity. And if you want, you can put these two results together. Logarithm of the square root of z minus 2 divided by z evaluated between minus I infinity to I infinity. Or if you want, log square root of 1 minus 2 over z evaluated between minus I infinity to I infinity. Now we have to be careful, very careful, because in the integral, in the starting integral here, the integral of this function dz from minus I infinity to I infinity is equal to the sum of these two integrals here. We have to be very careful here because when we integrate from minus I infinity to I infinity, there is a discontinuity. The discontinuity is at z equal to 0. So this integral here is problematic, is troublesome. But we can still accept this result if we rewrite it by using a limit. And this is the limit. Let me show you. The logarithm of the square root of 1 minus 2 over z from I 0 minus to minus I infinity plus we have the same here, logarithm of square root 1 minus 2 over z from I 0 plus to I infinity. This is the result that we have to accept. We cannot accept this one here because there is a discontinuity contained in the region of integration. So we have to split the result in these two parts and take the limit. We have to exclude the point I0. We can take I0 minus and I0 plus, but we have to exclude the point I0. So I didn't say that before. I should have, but I wanted to keep things as short as possible and avoid writing out too many expressions, because in that case I should have split this integral here in two parts by excluding the point I0. Okay, so you get the idea. I prefer to do it now. And now when we consider, for example, this one, we have to be careful again. We have to be careful again because there is still a limit. We have to calculate the limit as z goes to I0 minus here of the expression logarithm of square root of 1 minus 2 over z and subtract this same expression, but instead of z I have to replace minus I infinity. But in this case it is quite easy because when I replace z with minus I infinity, this term here will go to 0. It will be a complex number with a 0 magnitude and it will be negligible with respect to this. So I will have the logarithm of square root of 1, but the logarithm of square root of 1 is just 0 because it is logarithm of 1. And similarly for this one, in this case I have to consider only this limit of integration, the lower limit, because the upper limit will give 0 contribution. So I have minus log square root of 1 minus 2 over z, and I have to take the limit here as z goes to I0 plus. But now I can use a trick because the limit, for example, this one on the right, where z goes to I0 plus, can be transformed into a limit as z goes to I0 minus, but in this case, inside the square root, I have to change the sign. Here, I have a plus instead of a minus, because this one will change sign. It means that z will change sign, therefore I have to change the sign here. And now I can put these two limits together. I have limit as z goes to I0 minus logarithm of square root of 1 minus 2 over z divided by 1 plus 2 over z. And this can be rewritten as the limit as z goes to I0 minus of logarithm of square root of z minus 2 divided by z plus 2. And this can be rewritten like this, equal to limit as z goes to I0 minus, and then here I can put minus log of the square root of the reciprocal of this fraction, so I can rewrite it as z plus 2 divided by z minus 2. And now if I set z equal to 0 in the limit, this will be minus logarithm of square root of minus 1. But now the square root of minus 1 can be rewritten as e to the I pi over 2. and therefore the logarithm of e to the I pi over 2 will give me I pi over 2. So the result will be minus I pi over 2, which is exactly the result that we wanted. Of course, in this case, we had to resort to very informal steps, and it is not really clear how to do the derivation if you don't know complex analysis. There is some ambiguity also when you define the square root of minus 1 in terms of the complex exponential, because you can also rewrite square root of minus 1 as e to the I pi over 2, and then you can also add a multiple of 2 pi I. For example, you can add 2 pi I here. This is still equal to this, but this is e to the I 5 over 2 pi. And if you take the log of e to the I 5 over 2 pi, you will get I 5 over 2 pi, right? This kind of ambiguity can be eliminated if you define the complex logarithm in the interval minus pi, pi. So this can be eliminated, but it is less clear, for example, why I had to do this step. Because at this step I consider this minus sign, which helped me derive the minus sign here and also the minus sign here to get the right answer. Had I chosen to take the limit at this step, I would have gotten the same result but with a plus sign instead of a minus sign. So it is not so clear, if you don't know complex calculus, how to proceed. It is possible to derive also this minus sign in another way. You can try to do that by considering the sign of the imaginary part. And if you manage to understand that that imaginary part should be negative, you can try to avoid using complex calculus, but I think that it's more complicated, so what's the point of that? It's just to show you that by reasoning it out, you can find your way to tackle this kind of integrals.